Nonparametric regression. Smoothing models. In regression, given the training set x equals to the set x to the t r to the t, where r to the t is in R, we assume that r to the t is equal to g of r to the t plus epsilon. In a parametric regression, we assume a polynomial of a certain order and compute its coefficients. That minimizes the sum of a squared error on the training set. Non-parametric regression is used when no such polynomial can be assumed. We only assume that closed x have closed g of x values. As in a non-parametric density estimation, given x, our approach is to find the neighborhood of x and average the r values in the neighborhood so to calculate g hat of x. The non-parametric regression estimator is also called a smoother, and the estimate is called a smooth. There are various methods for defining the neighborhood and averaging in the neighborhood, similar to methods in density estimation. We discussed the methods for the univariate x. They can be generalized to the multivariate case in a straightforward manner using multivariate kernels as in density estimation. Running mean smoother. If we define an origin and a bin width and average the r values in the bin as in the histogram, we get a regressiogram. See figure 8.7, that is g hat of x is equals to the summations of b of x to the t times r to the t summing for all t starting from 1 to n, then divided by the summations of b of x to the t only, without multiplying r to the t, again summing for all t starting from 1 to n, where b of x to the t is equals to 1 if x to the t is the same bin with x and is equal to 0 otherwise. Having discontinuities at bin boundaries is disturbing, as is the need to fix an origin. As in the naive estimator, in the running mean smoother, we define a bin symmetric around x and average in there, figure 8.8. That is 8.20. G hat of x is equals to the summations of w of x minus x to the t divided by h. Then times r to the t, again summing for all t starting from 1 to n, divided by the term of the summations of w of x minus x to the t divided by h only, summing for all t starting from 1 to n, and where w of u is equals to 1 if the absolute values of u is less than 1 and equals to 0 otherwise. This method is especially popular with evenly spaced data, for example, time series. In applications where there is noise, one can use the median of the r to the t in the bin instead of their mean. Kernel smoother. As in the kernel smooth estimator, we can use a kernel given less weighted to further points, and we get the kernel smoother. See figure 8.9. Figure 8.9 is the kernel smooth for various bin lengths. So g hat of x is equals to the summations of k of x minus x to the t divided by h times r to the t, summing for all t, then divided by the summations of k of x minus x to the t divided by h, summing for all t. Typically, a Gaussian kernel k dot is used. Instead of fixing h, we can fix k, the number of neighbors. We don't know if this is good. Adapting the estimate to the density around x and get the KNN smoother. Running line smoother, instead of taking an average and giving a constant fit at the point, we can take into account one more term in the Taylor expansion and calculate a linear fit. In the running line smoother, we can use the data points in the neighborhood as defined by h or k and fit a local regression line. See figure 8.10. In a weighted running line smoother known as LOES, instead of a hard the definition of neighbors, we use kernel weighting such that distant points have less effect on error. So figure 8.10 is running line smooth for various bin lengths.